In this video, I'm going to be demonstrating the use of multi-factor key derivation within a fully decentralized application. Specifically, I'm using MFKDF in a portable cryptocurrency wallet that can be accessed with normal authentication factors like a username, password, and other secondary factors, all without requiring any centralized infrastructure. To get started, I create an account and choose a password. In this case, the wallet key is derived from a password, a YubiKey for 2FA, and a recovery code. But there are dozens of supported factors to choose from. Here, the application has gone ahead and created the other two factors for me, so I'll just click Finish. And I'm brought to my wallet where I can see my Ethereum address and balance. Because MFKDF is a completely trustless mechanism, it requires no client-side retention of secrets. And anything that does require long-term persistence, like the MFKDF policy document, can be safely stored in public view, like on a public blockchain, for example. This makes it an incredibly useful tool for encryption and authentication in trustless decentralized systems. In our case, when the wallet is created, the MFKDF policy document is uploaded to IPFS. An IPNS record is created to point to the latest version of the policy document. The fixed address of this IPNS record is effectively your username. A number of IPFS pinning services are then invoked to pin the latest version of the IPFS record. Back at the dashboard, right now I'm on the Ropsten testnet, but I can also switch to the mainnet. In addition to Ether, there are a number of ERC20 tokens I can manage and transfer as well. I'm going to go back to the testnet and transfer some Ether into this wallet to demonstrate. After a while, the transferred Ether is reflected in my balance. I'm now going to close my wallet and log back in. And because nothing is stored on the client side, I could even be logging in now on a completely different device. I'll enter my username, which is my IPNS address, my password, and use my YubiKey to generate a one-time code. Again, we used YubiKey here as an example, but MFKDF supports lots of other factors like TOTP and HOTP. So when I click Continue, my browser will locate the IPNS record, fetch the MFKDF policy from IPFS, and then use MFKDF to derive the key. But all of this is transparent to the user who essentially just thinks they're performing a normal login process. And just like that, I'm back at the dashboard and my Ether is safe and sound. And I could now go ahead and transfer it somewhere else if I wanted to. But I want to log out one more time to showcase that we're actually using a 2 of 3 threshold MFKDF key. So if I lost my YubiKey, for example, I can use my recovery code to recover the key. Same goes for losing the password, so any two factors are sufficient. If I wanted to change my password to something else, I could do that by creating a new MFKDF policy, uploading it to IPFS, and then updating the IPNS record and pins to point to the new policy. In fact, this process actually happens on every login when using one-time factors like YubiKey, HOTP, or TOTP. And we're back in. So to summarize, we have all of the features we love about centralized wallets like portability, recoverability, and multi-factor authentication with convenient, familiar authentication factors, while also having all the benefits of a trustless, decentralized, non-custodial wallet, made possible by multi-factor key derivation. We would never consider using password-based key derivation for such an application, due to the relatively low entropy and ease of brute force attack. But with over 150 bits of entropy, the multi-factor key derivation setup used here is trillions of times harder to brute force, and provides sufficient security for holding valuable cryptocurrency. But that's about it for the demo. Please feel free to try it out for yourself at wallet.mfkdf.com.